This is a triangle, and this, and this are the three x circles in the triangle. Their tangency points with the sides are here, here, and here. And then we draw perpendicular lines to each of the sides at the point of tangency. So this line perpendicular to this line perpendicular to this line, again at the point of tangency, and this line perpendicular to this line at the point of tangency here. We need to prove that these three red lines intersect at one point. This point is called the Bevan point for the triangle. We know that if we have a triangle and 3 points, one on each side of the triangle, and then 3 perpendiculars are being dropped, that these 3 perpendiculars intersect at one point if and only if x1 squared plus y1 squared plus z1 squared equals x2 squared plus y2 squared plus z2 squared. And we're going to apply this here. In this case, x1, so this distance, would be this distance from this point to this point. But this we know that it's the semiperimeter minus this side. Similarly, this segment is the semiperimeter of this triangle minus this side. This segment is the semiperimeter minus this side. This segment is the semiperimeter minus this side. This segment is the semiperimeter minus this side. And this segment is the semiperimeter minus this side. So if we call the sides of the triangle A, B, and C, then this is S minus A, S minus C, S minus B, S minus A, S minus C, and S minus B. And therefore, these three perpendiculars intersect at one point if and only if S minus A squared plus S minus B squared plus S minus C squared equals S minus B squared plus S minus C squared plus S minus A squared. But then all the terms cancel out. And therefore, these three perpendiculars to each of the sides intersect at this point, which is called the Bevan point for the triangle. This is the optional problem. We have this triangle with in center this point and circumcenter this point. This here is the Bevan point. As you can see, these are the parts of the x circles of the triangle which touch the sides at this point, and this point. And I've drawn the perpendiculars from each of these 3 points to each side of the triangle. So they intersect, we know that they intersect at the Bevan point. We have to prove that the incenter, the circumcenter, and the Bevan point lie on a straight line. And here's the solution. First of all, let's mark this side A and this side C. Then we know, because this is a tangency point of the incircle, that this length is the semiperimeter minus A, and this length is the semiperimeter minus C. On the other hand, because of these tangency points of the x circles, we know that this is the semiperimeter minus A, and this is the semiperimeter minus C. Now, since this is the circumcenter of the triangle, we know that this equals this, and that this equals this, which means that this triangle is isosceles, and this triangle is isosceles. And so if I drop the altitudes in these isosceles triangles, this will be a midpoint of this side, and this will be a midpoint of this side. Now, since this equals this, and this equals this because of the midpoint, we know that this small segment equals this small segment. And similarly, this small segment equals this small segment. Because this is C divided by 2, and this is semiperimeter minus A, we know that this is actually A minus B divided by 2, and this is also A minus B divided by 2. And similarly, this is C minus B divided by 2, and this is C minus B divided by 2. So now that we know that this equals this, and this equals this, we're ready to prove not only that these 3 points lie on a straight line, but that this point is the midpoint of the segment defined by the incenter and the Bevan point. See that we have this situation here, moved here on this side. Here we have a midpoint of this segment and a midpoint here of this segment, and here we have a midpoint of this segment here and a midpoint of this segment here, and here we have from each point we dropped a perpendicular, and like this, and then here from each point we dropped a perpendicular to the corresponding side like this and like this. And we need to prove that these 3 points lie on a straight line, and so similarly here we need to prove that these 3 points lie on the same line. So proving this problem essentially comes down to proving this one. Suppose that the line defined by this point and this point intersects this line here at this point. If we prove that this point and this point coincide, then we're done. To do this, I'm going to drop a perpendicular like this to this side, and I'm going to prove that this point coincides with this point, which would mean that this point would coincide with this point. Here, I've dropped perpendiculars from this point to this line and this line. We know that this line and this line are parallel because of the 90 degrees angles here and here. And so this line intersecting 2 parallel lines means that if this angle is 90, then this angle is also 90. And similarly, we know that this line is parallel to this line because of the 90 degrees here and here. And so if this is 90 degrees, then this should also be 90 degrees. And hence, we get some rectangles in the picture. This rectangle, and this rectangle. Therefore, this length equals this length equals this length, and this length equals this length. In this triangle here, this is a mid-segment, because this is a midpoint, and this line is parallel to this line. Therefore, this point is actually the midpoint of the blue segment, and hence, this becomes the mid-segment in this triangle, because we have a midpoint and a parallel line to this one. Therefore, this point is the midpoint of this red segment, meaning that this equals this. So now the large segment here equals this segment because of the original midpoint, which equals this segment because of the rectangle here, which equals this segment because of the midpoint we just found, which equals this small segment here because of the rectangle that is here. And so this small segment equals this large segment, meaning that the distance between this point and this point is 0, which means that this point and this point coincide, or this point and this point coincide, meaning that this point, and this point lie on a straight line, such that this is the midpoint of this segment.